In this section, we'll be talking about differentiation and integration of exponential functions. Now, we've already talked about logarithmic functions, and in particular, the natural log function. You know, I find this a little bit peculiar in the sense that, or interesting, in the sense that in algebra, when you talked about exponential and logarithmic functions, you talked about exponential functions first in a rather general way, and then you talked about logarithmic functions in a general way, and then you talked about those specifics of natural log function and the natural exponential function, or an exponential function with the natural base e. Well, I'd like to help with the understanding of this calculus experience. I think it would benefit us to go back a little bit and talk about how this subject was developed algebraically in the algebra experience, and get a kind of a broad view of it and a nice grounding with this, a nice foundation, and then bring ourselves up to what we have in mind for this section. When you first started talking about exponential functions, you defined an exponential function generally as a function of the form f of x is a to the x power. Now notice the variable is in the exponent. That's the real kicker here in this kind of function. A is a constant of some kind, and a is positive and not equal to 1. Now, this is the graph of 2 to the x power. And there were a number of characteristics that were discussed, and I'll just run through a few of them here. You'll notice that if a is greater than 0, then the graph tends to rise. It's an increasing graph. All of the graphs that you talked about at first went through the point 0, 1. And the difference in the graph that occurred when you change the value of a, now let's assume that a is greater than 1 for a moment, but as we get larger and larger than 1, 2, 3, 4, 5, the graph tends to go up even more dramatically right through here. And as this base tends to come down to 1, that is, it decreases and approaches 1, the graph sort of lays down like this. It has this kind of appearance. It has more of a gentle curve to it. Then when the values of a appear between 0 and 1, the graph decreases. The graph goes down like this. And there were some other characteristics as well. The functions are continuous. They're 1 to 1, as we can see, continually increasing or decreasing, so they're 1 to 1. And therefore they have inverses, and we're going to get to the inverses in just a little bit. But that's how the idea and structure of exponential functions started. Then you moved into the idea of solving exponential equations, and this was a lot of fun, especially at first. You had equations like 2 to the x is equal to 8. We want to find the value of 2. That is, what exponent on 2 will give us a value of 8. And it's pretty easy to tell that 2 cubed is 8. But the structure of solving these equations, the general idea, the concept was to cause the bases to look alike on both sides. So we could write 8 as 2 cubed. When the bases are alike, we jump right into the exponential world. So x is equal to 3. Now with that idea, you can solve equations like this. What's the exponent on 4? Such that 4 to that exponent is equal to 8. Not as trivial as the one before. But it's pretty easily solvable when we rewrite on both sides to cause the bases to be the same. We can write 4 as 2 squared to the x power is 2 to the 2x, and 8 is 2 cubed. Now the bases are alike, so boom, we jump right into the exponential world. 2x is equal to 3 then, so x is 3 halves, or 1 1/2. Then we can solve problems like this. 5 to the x plus 1 equals 1 over 125. Well, 125 is 5 cubed, so this is 5 to the negative 3 on the right side. And this is 5 to the x plus 1. Bases are alike, boom, we jump into the exponential world. So we have x plus 1 equals negative 3, or x is negative 4. Negative 4, remember, is the number that would replace x here to make this true. Okay, then we bumped into a certain kind of equation like this. 2 to the x power equals 5. And our technique for solution breaks down because we can't very easily rewrite these bases to be alike. We can't express 5 as 2 to some exponent. So it's kind of like the ticket window to the exponential world is closed on us. Now we need to reopen it. And you reopen it by jumping into the world of logarithms, because indeed the world of logarithms is the world of exponents. Now when you first started talking about logarithms, all you did was talk about an exponential form and a corresponding logarithmic form. And that discussion went kind of like this. The exponential form is 3 to the x equals 7. The corresponding logarithmic form involves log, and there were 3 positions here to be filled, 3 places. And this is a base, and that's an exponent. So let's see, the base here is 3 and the exponent is x. So the 3 goes in this position and the exponent x goes in this position, and we fill this number right here. And for no seeming rhyme or reason, this is just the position of those 3 numbers from the exponential form. And that's all we did. And it was very confusing at first, if you recall. Well, let's see. Let's try it some more. I want to make sure we understand this transition. We need to go from exponential form to log form, from log form to exponential form very freely and easily. And we'll see why later. But let's do another one from exponential form to log form. X to the 5th equals 12. Well, log, now base is x. The exponent on that base is 5. So the exponent is over here, and the number 12 goes in this position. So this is the log of 12 in base x is equal to 5, corresponding to this exponential form. Now let's go from log form to exponential form, base exponent. So this says 4 to the x power equals the number 6. And this in exponential form, base exponent, so 3 to the 5th is equal to x. Now notice that in all of these logarithmic forms, when you talk about the log of a number, it is equal to the exponent from over here. That number is an exponent. So a logarithm, the logarithm of a number, is an exponent. A logarithm is an exponent. Very important idea when you're dealing with logarithms. And because logarithms are exponents, they follow the rules of exponents. That is, in the world of exponents, when you're multiplying like bases, you add exponents. When you divide like bases, you subtract exponents. And that corresponds with properties of logarithms. Here, for example, the log of 5x, these are properties. Sometimes this is called the multiplication rule or the product rule or the product property, whatever. But you learn that the logarithm of a product is equal to the log of one factor plus the log of another factor. Now, notice that I didn't put a base on the logarithm because the base doesn't make any difference. As long as the base is the same for all these, this is all proper. This could be base 5, base 10, base e, base whatever, you see, and this property holds true. So, and this corresponds with, and it can be shown to correspond with, we can prove this using our ideas of exponents. Okay, then the logarithm of a quotient is the logarithm of the numerator minus the logarithm of the denominator. And these things don't seem to make a great deal of sense until you realize we're talking about exponents. All right, so, and the log of x cubed is 3 log x. That is, the 3 becomes the coefficient of the logarithm. This corresponds with the idea of raising a power to a power, and it's called the power rule for that reason. Well, with all of this information and with this kind of ammunition, we can solve that little problem that we talked about earlier, that 2 to the x is equal to 5. Let me show you that solution right quick. All we do is apply the operation called logarithm on both sides of this equation. Now, there are other ways to proceed here, but I'm just going to show you the most direct way. And it's kind of like squaring on both sides or taking the square root on both sides. We're just applying an operation called logarithm on both sides of the equation. So it's log 2 to the x equals log 5. Now notice I'm not designating a base of the logarithm. When a base is not designated, it's understood to be 10. I could just as easily now use ln 2 to the x equals ln 5, and that base would be e. We'll have a lot more to say about that in a little bit. But at any rate, using the power rule here, this becomes x log 2 equals log 5. And log 2 is just a number in the calculator, so it's a coefficient of x, and we divide on both sides by that coefficient. So x then is log 5 over log 2. And again, we just punch the calculator here to get our answer. Now don't make the mistake of thinking that we can cancel the two logs here. That would be kind of like canceling radical signs or something like that. It's an operation that is being described here. Or we can think about it like that. So x then is this quotient, and punching the calculator we find x to be, and I should say approximately, equal to 2.32. So the exponent that is on 2 to give 5 is 2.32. I want to make sure we understand that log x means log base 10 of x. And ln x, the natural log of x, means log base e of x. These are two so familiar, these bases, logarithmic bases, are so often used that they sort of have abbreviations or nicknames or something like that. And these are also the ones that appear on the calculator. Now, some evaluations involving logarithms should be automatic for us. For example, ln e, or the log of some number, and the base is the same. So this is base e and e. And it would be the same if we had log base 7 of 7. What is that equal to? It's the same amount. Well, we can figure it out like this. Let's figure it out for natural log. Now, I'm just going to take ln e and set it equal to an unknown value like n. And then we're going to jump into the exponential world. And it's often the case that when we're solving logarithmic equations, we go into the exponential form. And when we're solving exponential equations, we go into the logarithmic form. It's an interesting idea there, and that's why they kind of march together through their mathematical involvement. At any rate, for us to write our exponential form, I'm going to emphasize the base of the logarithm here. So it's e to the n equals this number, it's e. And this e is raised to an understood 1 exponent. Since the bases are alike, we know that n is 1. So if n is 1, now we set this equal to n. If n is 1, then this is 1. So log base 7 of 7 would be 1. Log base 10 of 10 would be 1, and so on. Now another item that ought to be familiar, that ought to be easy to calculate, is ln1. We probably already know what this is, but I want to make sure. And it's the log of 1 regardless of base, but we'll use ln for the demonstration here. And again, I would do this. I would say let ln1 be equal to n, and let's go into the exponential form. So the base here is understood to be e, so it's e to the n power is equal to 1. Now what value of n can we put in here for e to be raised to that exponent and the result to be 1? It turns out that n has to be 0 for this to occur. So if n is 0, n stood for this expression, so this is 0. And the log in any base of 1, the log of 1 in any base is equal to 0. Okay, rather important idea. Now, we're seeing this relationship between exponential form, logarithmic form, and the relationship is intertwined in a lot of different ways. One way is that every logarithmic function has an exponential function as its inverse, and every exponential function has a logarithmic function as its inverse. Let me generate a couple of inverses for you. Suppose we take this exponential function, e to the x. And by the way, when I was talking about exponential functions earlier, I didn't specifically talk about e as a base of an exponential function. I did it in an earlier discussion, but I want to make sure we understand that e is a very important base of an exponential function. If we look at something like, let's see, two to the x power, we look at 3 to the x power. one explanation for the origin of E, or a way to explain E, or how does E come about? It's a naturally occurring constant, it's an irrational value, has to do with this. And recall that at this point 0, 1, there is a slope of the tangent line at that point for this graph and a slope of the tangent line at that point for this graph. And it turns out that the slope of the tangent line for this graph is a little bit smaller than 1. And the slope of the tangent line for this graph at that point is a little bit larger than 1. And the base of an exponential function that produces the slope of a tangent line at that point to be exactly 1 is that base E. Okay, so that's an explanation for it. There are others. Let's see. So if we have f of x is e to the x power, we write this as y is equal to e to the x power. The inverse means to swap the role of x and y and solve for y. So we do that. We swap the role of x and y. We want to solve for y. To get into the exponential world, we go into the logarithmic world, because indeed the world of logarithms is the world of exponents. Okay, so the logarithmic form of this is log, let's see, base exponent. So base exponent. And log of base e is ln, natural log. So this is ln x is equal to y. Y equals ln x. So here is our inverse of the exponential function. So it's f inverse of x is ln x. Let's do it the other way. Let's call this by a different name. G of x is ln x. And let's generate the inverse. All right, so it would be y equals ln x. Swap the role of x and y and solve for y. To solve for y, since we have a logarithmic function here, we would, or a logarithmic kind of relationship here, we would go into the exponential form. Base is e, exponent x. So e to the x equals y, and swap it around, and this then, y equals e to the x, y is a function of x, is the inverse function. G inverse of x then is e to the x power. Now, as a result of that kind of relationship, we know then that if this is the graph of e to the x, and we know we have this reflection into the y equals x line, then we know that the logarithmic function would have this as its graph. And you might verify this by punching it into your calculator. Notice the swap of domain and range here also. The domain of this function is all real numbers, and the range would be values that are greater than 0. And swap those ideas for the natural log function. For the natural log function, the domain would be values greater than 0. See, we can only take a log of numbers that are positive, and the range would be all real numbers. All right, with this information about logarithms and exponential functions, we can solve certain equations like this. The first thing we ought to notice is that we have an exponential function because we have a variable in the exponent. And we notice that the base is e. Now that's only important because in order to get to this, the exponential area, or into the exponential world, we apply logarithm on both sides of the equation. And we can apply any type of logarithm we want. We can apply logarithm base 7, logarithm base 10. Doesn't make any difference. However, it's a little easier if we see a base of e. We would apply natural log on both sides. So we'll just go ln 7 equals ln e to the x plus 1. Now with the power rule, the x plus 1 becomes the coefficient on the right. And this ln e goes out. Remember, ln e was 1. And that's the value of using natural log when we have a base of e to start with. We could have used log on both sides, and we would still calculate this to the correct value. But we would have a constant in this position that we would have to deal with. We would have to divide it on both sides, and it would all come out in the wash, but it's just easier like this. Well, so on the right, then, we have x plus 1, and we'll subtract 1 on both sides, so we have ln 7 minus 1. Now, I don't want to imply that this is 7 minus 1. It's ln 7 minus 1. It's kind of like this, equals x. And when we punch the calculator on this, we find x to be, approximately 0.946. Now let's evaluate this. This is kind of a special form. You'll notice that we have the natural base e, and in the exponent we have ln. You see, we have natural log, and this is kind of a special form, and a special kind of thing will happen from this. Well, to evaluate it, I'm going to set this equal to a letter like let's say n, and we're just going to evaluate this expression. Well, to evaluate, we can jump into the exponential world if we want to, or excuse me, the logarithmic world, by applying natural log on both sides. This is ln e to the ln 5 equals ln n. Now, this becomes the coefficient. ln 5 is the coefficient then of ln e, kind of like this. And ln e is 1, so ln 5 equals ln n. Now, suppose we have an operation at our disposal called anti-logarithm, undo logarithm. So we have the logarithm of something on both sides. These logarithms have the same base, so we can undo logarithm on both sides to that base. And we have then that 5 is equal to n. So n is 5. If n is 5, then this evaluates to 5. That is, e to the ln, let's say x, is equal to x. It's whatever that is. Now, this kind of idea helps us. We can go the speedy way through a problem like this. E to the ln 2x, well, this expression is just 2x. You see, so very quickly, we can evaluate this to be 6. Here's another one. Now, you may notice that in solving that exponential equation, we use logarithms. To solve an exponential equation, you often go into a logarithmic kind of form. And vice versa. When you have a logarithmic form, and here we're solving, we have a logarithmic form, we often need to go into the exponential form. Now, not always. In this evaluation right here, where we had ln 5 equals ln n, we didn't have to go into an exponential form because we had logarithm on both sides. But here, we don't. And so we need to go into the exponential form. Okay, the exponential form, now let's understand that this is base e, so this is e to the 5th power equals 2x minus 3. Now, e to the 5th power is just a number in the calculator. This is just a constant of some kind. So we're going to treat it like that and solve for x. So it's e to the 5th plus 3 equals 2x, or e to the 5th plus 3 over 2 equals x. And then punching the calculator for this, we find x to be approximately 75.707. You'll be delighted to know that the derivative of e to the x is e to the x. That is, if f of x is e to the x, then f prime of x is e to the x. Interesting. Graphically, it's kind of like this. We have our graph of e to the x. We have a point here like, let's say 2. And then this distance would be e squared. And the slope of the tangent line at that point is also e squared. Very nice, easy correlation. That's one of the grand characteristics about this exponential function with base e. Okay, now if the exponent is not just simply x, if it's a function of x, if it's an expression that's a function of x, that is, it's e to the u, then the derivative is e to the u du dx, chain rule. Or I kind of prefer a notation like this. The du dx is really u prime, so it's e to the u times u prime. So something like this would be real easy to calculate. If f of x is e to the 2x minus 1, then f prime of x is e to the 2x minus 1 times the derivative of the 2x minus 1, which is 2. So it's 2 times e to the 2x minus 1. Let's work a few problems. We have y is e to the negative 3 over x. Now all of the problems that we're going to work is they just become a matter of manipulation, and sometimes the manipulation is simple and sometimes it's a little challenging. But here, for example, we're thinking of this as the u. So we might write this as e to the u power, and we know that the derivative here is e to the u times u prime. So we would probably go over to the side and make a calculation about u prime. If u is negative 3 over x, then this is negative 3 x to the negative 1. And u prime then is, let's see, negative 1 times negative 3, that's 3 x to the negative 2, or 3 over x squared. You see, so we come over here and we very carefully make our calculation about u prime, and then we can come back into this environment and make a replacement. So e to the u, replacing u with negative 3 over x, the u prime is 3 over x squared, and then clean it up by multiplying. In the numerator we have 3e to the negative 3 over x, and in the denominator x squared. We could manipulate it even further, you see, with the negative exponent here. Here's another one. Y is e to the x minus e to the negative x, all over 2. Now we're going to take the derivative, and we would like to look at separate terms here, so we would probably manipulate a little bit like this. We would divide 2 into both parts here, like this. We would probably write this with a distinct coefficient of 1/2 in both places. And now taking the derivative, let's see, the derivative of this is just 1/2 e to the x. You see, because the derivative of the x is simply 1 if we're thinking in terms of u. And then over here it's 1/2 e to the negative x times the derivative of this, which is negative 1. So negative 1 times negative, that's positive, so we get this, and we're back into this kind of form. It turns out that the answer here is remarkably similar to the problem that we started with, but in view of the idea of derivative in this environment, it's not too surprising. Here's another one. It looks like this one that we just did, but it involves natural log. Now let's remember our derivative of logarithm idea. It was the derivative of ln u is u prime over u. Remember that? So it's here, it's ln of this. Now we're going to put this in a more palatable form using our law of logarithms. So it's the logarithm of the numerator minus the logarithm of the denominator. Okay, now for the derivative, it's the derivative of this minus the derivative of that, and this goes out because it's a constant, so that's out of here. So let's see, ln, now think of this as u. So it's the u prime over u idea that we're looking for. Now u prime means we're taking the derivative of this. So the derivative of e to the x is e to the x. The derivative of e to the negative x is e to the negative x times negative 1. You see, a real simple idea. And then the negative 1 times the plus gives a minus sign right here. And the u in the denominator just kind of we replace this down. So we come right down with this right quick. Now this is an answer that may be acceptable in some situations. However, when you work problems like this and you look to check your answer in the back of the book, you might find an answer in the back of the textbook that looks quite a bit different from the one that you got. And it's not necessarily because you did the problem wrong. It may be because you didn't manipulate it into the form that's given in the back of the textbook. For example, in this one, we could continue the manipulation process by thinking about these negative exponents, you see. So e to the negative x is 1 over e to the x. So we could change the numerator into this, change the denominator into this. Now we want common denominators here and here. So to change to the common denominator e to the x, we'll multiply by e to the x over e to the x. Well, this then becomes e to the 2x over e to the x. And in the denominator, the same idea. Multiply e to the x over 1 by e to the x over e to the x. So we get e to the 2x over e to the x. Now we have common denominators here, common denominators here. When we collect, it's e to the 2x minus 1, and down here, e to the 2x plus 1. And both of those fractions are over e to the x. Let's continue up here. So e to the 2x minus 1 over e to the x in the big numerator, and in the big denominator, e to the 2x plus 1 over e to the x. Well, this is fraction divided by fraction, or fraction times the reciprocal of this. So it's the numerator, big numerator fraction times the reciprocal of this becomes this. The e to the x's cancel, and we have e to the 2x minus 1 over e to the 2x plus 1. Now, I showed you the manipulation because if you saw this in the back of the text and your answer is this and you think that's your final answer, you might not recognize those as being equivalent. So you might have to go through some manipulation to put the problem into the same form that you see when you look at your answer in the back of the text. Since the derivative of e to the x is e to the x, the integral of e to the x is e to the x plus a constant. So we could write this. Now, the integral of e to the u du is e to the u plus a constant. The trick in dealing with this situation, we'll go right to the situation of the u, where u is an expression involving x. But the trick in dealing with this is to take care of the du part. For example, the integral of e to the 3x plus 1 dx. Well, we think of this as the u, and we might come out to the side and actively think and write down u is 3x plus 1, so du is 3 dx. Now, 3 dx is what we want to appear right here, you see, to have the du form. So let's see, we need a 3-factor. We can accomplish a 3-factor by multiplying by 1/3 out here and 3 inside. So 1/3 out here, 3 inside. This is the form we need. So it's e to the u du, you see, and therefore the integral is e to the u, or e to the 3x plus 1, and it's multiplied times 1/3, and we add a constant. Now, there are a couple of different ways of handling this substitution. Here we just pretty much did it mentally. Let's take a look at another problem. We have the integral of 5x e to the negative x squared dx. And as soon as we see a constant involved, I suggest we just snag it out and write it outside of the integration. Okay, now we're thinking in terms of, we've got e to the negative x squared, we have an x factor here, we have dx. Well, we know this is going to be the u part. So we might come out to the side and say u is negative x squared. Du then is, well, the derivative of this, negative 2x dx. All right, so we need to have all of this, and what do we have? Well, we have dx, we have x, so we have x dx. Now, to emphasize what we have, we might rewrite as the x dx next to one another like this, and even emphasize that's what we have. And what we need is negative 2x dx. Okay, we can accomplish the negative 2, pop the negative 2 in here if we have a negative 1/2 out here. And that's the way we proceed. Now we have the form that we want, e to the u du, and so we have the integral of e to the negative x squared is negative e to the negative x squared. So we have this, and then we tack on the constant. Now there's another way to proceed here, and some people prefer to make an active substitution. And let me go through the process with the same problem and just step through the logic pattern for that. We start in much the same way. We have 5x e to the negative x squared dx. All right, we snag out the 5 right quick. We probably would be wise to resort the other factors so that we have e to the u, you see, separate from the other factors. So, and I've done that here. All right, now it's at this point in the problem that we would come out to the side and say, all right, u is the negative x squared, the du is negative 2x dx. Now what we have in our problem is the x dx. So what I could do over here for substitution purposes is I could solve this for x dx. And to solve that for x dx, this is du over negative 2 equals x dx. All right, now I can rewrite over here, replacing x dx with this fraction. Let's go over here and do that. So the x dx is the du over negative 2. And this, since the u is negative x squared, we have the u here. All right, now we want to accomplish the form over here to the right of the integration symbol is the e to the u du. So we need to snag out the negative 2. And since it's in a denominator, it manifests itself as 5 over negative 2 outside. Now we have e to the u du, so the integral is e to the u. And then we tack on the constant c. Then we back substitute. The u is negative x squared. So some people feel like this is a little bit cleaner, a little bit easier to see through if we make these active substitutions, but sometimes it adds a step or so to the problem. Here's another one. The integral of e to the 1 over x all over x squared dx. Now, let's go through that separation process right quick. That is, we want the e to the u part, we want to write that first, and then we want to write sort of everything else after that. So it's e to the 1 over x, and then move this x squared in the denominator over by writing it as 1 over x squared dx. Now we identify the u part as 1 over x, which is x to the negative 1. So du then is negative 1x to the negative 2 dx, but this is negative 1 over x squared dx. Now we could go through that substitution process, but we can understand that we want to be looking at this for the du part, and what we have is this, and they're very similar. All we need is a negative sign in here. So we'll just pop in a negative out here, a negative in here, and away we go. We have what we need, so it's e to the u, you see, or e to the 1 over x is the integral here, and we have our negative sign and we have a constant. Here's another one. This is a definite integral. It's the integral from 0 to 1 of e to the x over 1 plus e to the x dx. Now we might be looking for this opportunity to use the integral of e to the u du is e to the u plus a constant. We might be looking for that constantly right here because we have used it so many times. But don't lose track of the idea that we have performed integration in the past, and we have used different formats. We've looked for different kinds of structure in our problem. And on this one, if we separated out the denominator here and tried to use the technique from before, we would find out that, gee, it just doesn't work. If we think of this as u, we don't get anywhere with the du part of that. It just doesn't make any sense. So we can't get very far with that idea, but what we can do is think in terms of what we've had before, in terms of natural log. That is, if we can find the structure u prime over u, you see, the integral of u prime over u dx, that becomes the natural log of the absolute value of the denominator plus a constant. And we're pretty close to that right now. In fact, we have that right now because, after all, if we take this and take the derivative of it, the derivative of 1 plus e to the x is e to the x. So we have u prime over u dx right now. So this then becomes ln, absolute value denominator, you see, plus a constant, but since we've got a definite integral, we don't need the constant. So it's ln absolute value denominator, and then here are our limits of integration. So we go through and let's see, ln, and replacing the x with 1, we would have 1 plus e to the 1 or 1 plus e. And then minus ln, replace the x with 0, and e to the 0 is 1, 1 plus 1, 2, so ln 2. And here's our answer, and an approximation from the calculator would be 620 thousandths.